I want to talk about bare metal blinking using no SDK, although we will need to have Picotool in order to upload our application onto the Pico. Now, I've seen a lot of tutorials in the past that either use assembler, which is a bit fiddly, they use Rust or they use Zig or something else, and I thought, well, let's try and do something in C. What we're going to do is put a blink sketch onto the first 256 bytes of the flash. That's the boot 2 sector. Normally what happens in the boot 2 sector is that they'll set up things like flash and other stuff and then jump into the reset vector, and that will kick off whatever it is you want to do. But I'm just going to do a blink sketch using the 256 bytes of flash that are allowed in the boot 2. Now, there are complications involved that you don't actually have 256 bytes of RAM to work with. You only have 252. That's because 4 bytes need to be reserved for a checksum at the end. I'll get back into that a little bit later. But let's do a blink sketch. So let's look at the files that I've got here. So I'm going to look at main.c. No, not that one. The one.c. This is our blink sketch. Right. Now, I'm not using any libraries, so I want a uint32 type, but that's actually available as from the compiler, so I don't need to include anything. I'm just going to create a uint32 like this. Now I'm going to have well, actually, let's get to the main program. I think we have a simple delay function here. I haven't looked at the timings. It's just a rough and ready thing to do. So you put an integer, and we go around a couple of loops, operating a no-op, and that should act as a timing. So not that interesting. Here's the main function. Well, you can see the main here. It has a couple of attributes. The first one is naked. So what happens with traditional functions is you have a prologue and an epilogue. A prologue is like you push program counter. Sorry, you push. A prologue will be you push the link return address to the stack, and at the epilogue would be is at the end of the function you pull that address off and jump to that address. But we're not going to do that. We don't need that because we don't return from main. We just execute it. This section here, this is to do with the fact that we want to make sure we put main at a certain offset in the file. It has to be at the beginning because that's where the Raspberry Pi will boot to. You notice I defined delay before main. So if we hadn't messed about with this, what would be written to the binary file is the function delay before main, and that would just be wrong. It would call the delay function, and that's not what we want. The boot2.main, that's a special section defined by the linker, which we'll get into in a moment. Okay, so what do we need to do? Well, it took me a while to get this going, but we have a reset mask. Let's have a look at this section first. We have pad bank 0 and IO bank 0. These are the GPIO registers. I've actually got it defined up here. Okay, well, I'll maybe go back in a minute. What happens is that when you switch on the Pico, the whole thing's sort of like dead. There's no GPIO available or anything like that. You have to bring it up. So what you do is you want to bring up the pads in the IO bank. Right, that's in the resets mask. Now the resets, setting it equal to the complement of the reset mask, that means we want to bring it up. We're telling the Pico that we want to put these into an active state, and this is what the reset register does. Now, just because you do that doesn't bring these peripherals up straight away. And what happens is you need to wait for a while to check that the resets are done here. So if the reset is not equal to the resets mask, then we just keep looping until our peripherals are up. So this is what all this is doing. We're basically just getting the GPIOs up and running. Okay, that's a comment. This line here. We want GPIO pin 25 equal to GPIO function CO. Now, GPIO pins have several functions like SPI, I2C, PWM, and so on. We just want vanilla, straightforward GPIO pins, and this is what this value is. I'll perhaps go up a bit later, and we'll see how these are defined. We've got LED, which is value of 25. That's the onboard LED. CO GPIO set. In other words, we set this register with pin 25. This will allow it to go output. And now we have a while loop, which we just repeat the toggling on and off. So CO GPIO out set. This value for the LED. LED is the value 25. So in other words, this turns our LED on. We do a short delay. Similar here, we turn the LED off, but we set it to the, so we need to do that, we need to go to the GPIO out clear register. Then we delay for a bit longer. I like short flashes, and then we just go again. Repeat that loop. Let's just have a look at some of this at the top here. So you got this curious macro here called reg. That means that it takes an address, some address in memory, and it means that we can do things like resets, turn a number into address that we can use to set values of that address. So, well, I mentioned the resets. Let's go through this. So the resets base, that's defined in the RPR data sheet. That's address 4000C000 in hex. The resets reset, which I showed you before, is an offset from that base of 0. Okay, so not that interesting. The reset's done is an offset of 8. And well, there's the pads have similar addresses and so on and so forth. So that's the that's our program. But there are other bits to this too which make things a bit complicated. So let's have a look at the linker script. This is our link script. It's a bit arbitrary what we call this. I call it flash. We have an origin. Now the origin, this is fixed. It's specified in the data sheet. The length, well actually I could have put the length as 256 bytes. Actually, or 248 bytes, yeah. So you don't get to use the whole 2 meg because we're just using the flash, the boot sector. So I've got sections here. I've got boot2, I'm calling it, and here's the boot2.main, which we want to make sure was the main function is the first thing we see in our binary. Then we have the rest of it and we put this into flash. I don't think that's strictly necessary. Let's have a look at the makefile. Now there's a whole lot of stuff going on in the makefile, which I'll only briefly touch on. Well, we specify our assembler, compiler, some flags. We've got to make sure we use the right Cortex M0 thumb, a linker, that. We just want to actually compile led1.o from led.c. Now let's have a look down here. We don't create a UF2 file. I did find online a utility to convert a binary into a UFT2 files, but I'm not going to do that. I decided against that. I think we can just work with binaries and Picotool. That's what I've chosen to use. So normally I'm going to create an app.elf file, which is composed of a linker. It's a fairly normal link. Object copy from the elf file to the binary file, and I do a disassembly of that just for curiosity's sakes. This I can get rid of it because we're not using a UF2 file, and in fact the app.elf will be wrong. This app.uf2 file will be wrong due to the checksums. So we'll go back so we produce app.elf using these. Now we have this curious thing. We can't just upload app.bin to the Pico. We need to add a checksum. What the checksum does is when the Pico boots, it looks at the first 248 bytes on flash, then computes a checksum. The last 4 bytes in that 256. I'm going to get this right. 256 byte flash is the checksum. If the checksum doesn't agree with the values before that, then it won't execute what's in flash. Let's now I found files online that compute checksums, and they're all complicated, and I just decided to roll my own. And let's just have a look. have a look at checksum. Right, so the checksum is a CRC32 width number. For some reason it doesn't use a standard polynomial. You have to specify a polynomial that's actually given in the RP2040 datasheet along with an initial value. That's irrelevant, and that's how you do setting up here. Let's have a look at the rest of this. Well, so you load app.bin, you take the first 252 bytes, and in fact actually what you do is you have to expand the app.bin so that it is 252 bytes long. Otherwise you're not going to get 256 bytes at the end. You then calculate a checksum, which is 4 bytes in long, and you append that to your 252 bytes, and then you write it out. I've written it to a binary called sum. Right. If we used to do a difference between app.bin and sum.bin, we would find that they would differ in the last 4 places, padded out to 256 bytes. Let's just make it clean, because I've done something to bin. I'll show you the little tweak about the checksums. Now I'm going to make it again. Let's do make. Let's do make clean again. Let's do make. And so we do all that. And we have sum.bin. No, I don't think there's much we can do here. But this here is the checksum of all this. You know, according to the algorithm that we're supposed to use. So let's flash this onto the drive. I'm going to reset the machine. Oops. Things happen. Let's do it again. Okay, well, let's do make flash. Okay. And lo and behold, oop, we see blinking. Hooray! Oh, I'll just go over the makefile for flashing. So let's makefile. I didn't cover that, so let's have a look at that. Flash. We don't. This is the flash section. We don't apply that. Pico. Normally we could just copy the UF2 file to the device, but here instead we use Picotool to load our binary onto the flash, and then we do a reboot here. Now I'm going to mess up the binary. So we can write bless and we'll see what happens. It's a bit slow. Come on, what's going on? I'm going to wreck this binary. Recall here is the checksum. I'm going to set that to 0. I'm just going to wreck the checksum, and I'll save that. And the Pico's not going to like it, so let's reset. Let's reset my Pico. And now I'm going to make flash again. Right, so we've transferred it. Oh, did you see that? Okay, let me see again. Let's do a reset. So I'm going to press the run, which will reboot the machine. And look, no blinky lights. What happens is, if we can have a look, it's not doing it now. Aha, right, okay. So what happened is my folder is open, and what's happened here is this is my Raspberry Pi drive. What's happened is the Pico has checked the checksum, said, oh, that's not matching, so I'm not going to run that executable. So it just goes back into boot select mode. Let's just prove we can get things working. So we've recreated sum.bin. I'll flash it again. Right, now it should be working. Nothing. Okay, what's going on here? Let's make sum.bin again. Okay, it's redoing the checksum, and okay, it's restored. That bit there. Well, let's make flash again. Okay, so now this should be blinking. Let's have a look. And there we go. Jobs are good.